what we have here, David?
What this machine has been designed for is to deal with the screenings, as they call it, from a water treatment plant. In other words, anything that's flushed down the toilet that is a solid material that floats on the incoming sewage stream is caught by rotating screens, and it's gathered up and then fed out through an Archimedes screw into a containment vessel. That is what you see here. So basically what you have is a very variable feedstock which consists of textiles like baby wipes and so forth, and anything else that you might think of that is flushed down the toilet which is not actually sewage. Now, this material is very expensive to deal with for water companies because it costs anything from 100 to 200 pounds a tonne to dispose of in a licensed landfill, and there is a difficulty of transportation which is built into that. So if they can destroy this material on site without it leaving site, you've got several advantages. One is reducing the bottom line costs, but two is that you're containing a waste material within the site where there are very stringent safety regulations, as opposed to exposing it to a road haulage system. So if we can convert this, and not counting what we might get that is useful from the end result, then it is saving the water company on average around about £150 a tonne. Plus, it is extremely good for the environment because it is keeping this off the streets and containing it within a safe site. But in addition, if the calorific value of the material is high enough, and we designate around about 15 megajoules per kilogram and something less than 40% moisture, then we can convert this cleanly, without combustion, through a pyrolysis system into useful energy. Useful energy in the form of syngas, which is effectively breaking it down into its natural components. If this was put into a landfill, for example, as the landfill deteriorates with more material being put on top of it and pressure pressing it down, then it would break down into its natural components of hydrogen and carbon. Carbon in that case in the form of carbon dioxide. In the form of our case, we accelerate this under controlled conditions into hydrogen and carbon monoxide because we don't allow any oxygen into the system. So there can be no combustion, so there is no oxidation. The material is taken from there and fed into this feed hopper. Now, this feed hopper is not the normal permanent fixture. This is here for the sake of testing because the water utility want us to be able to sample different types of feedstock. So the testing will be a stop-start facility. Normally, this would be a bigger, more elaborate system, and there would be a mechanical handling system on the front end so that we would not be manually handling this material. But in this case, the material is put in here. Inside here is an Archimedes screw feed screw. The material is moved down this tube. At about this point, it's being compressed. The important thing is that we extract as much air, as much oxygen as we can, and we form a plug that seals the system, because the whole system of pyrolysis relies on there being no oxygen. If there is no oxygen, there is no combustion. Now I'll explain how that works in a minute. But about this point is where the compression takes place. Because the material is quite wet, a lot of water is squeezed out of it at this point here, and that is drained away, collected and drained away. Here we have a convergent nozzle, so the material starts to compress at this point. There is a back pressure built up here, so you're forming a solid plug in the pipework before it goes into the pyrolysis tube, which is at that junction there. Now the pyrolysis tube then picks it up because we have inside there a screw conveyor, another Archimedes screw. Both of these screws are infinitely variable in speed. We can change the torque. What we have done in this particular case is set up a pulsing system whereby we operate on a minute cycle. 10-minute compression and feed, and 10 seconds I should say, of compression and feed, and 50 seconds of standstill. The reason for that is that as you push this plug, you need a lot of torque. To get that torque, you have to increase the energy from the motor through the gearbox, which if you allowed that to go into the feed to the screw, it will be screwing too fast, it will be feeding too fast. So we put the torque into the screw to push the plug for 10 seconds, then it stops. And then the pyrolysis screw picks it up and then starts to feed the material up here. Then the process starts again. And then it's just enough to fill the cavity between the veins in the screw each time. So it's a cavity feed each time. The material starts on its journey up through the pyrolysis tube. About the first third of the pyrolysis tube is the material drying out. And then we set the point where the material starts to decompose into gas, hydrogen and carbon monoxide, nitrogen. And then as it continues its journey up the tube, the material is breaking down continually all the time until it gets to the top, where we expect approximately 90% of the solid material is converted to gas. Now inside that tube we have an Archimedes screw, we have an inner tube and an outer tube. The space between the inner tube and the outer tube we term as the hot box, because hot gas contraflows back down the hot box, down the space between the inner and the outer tube. So the hottest part of the tube is at the top and the coldest part is here, because that is where the raw material is going in and you have a contraflow. Now, under normal circumstances we'll be running this at around about 650 degrees centigrade, which is the ideal situation for causing the material to break down. But that is indirect heat. There is no flame, no combustion, that is just heat. So the material is passing through 650 degrees C of heat. That causes the material to break down as it would in a landfill, but we accelerate that process under control.
What different temperature profiles are there with regards to the types of feedstock?
It depends on the feedstock that we're operating on. The problem with this is that it's quite wet, so we would have to increase the temperature slightly so that we've got the bottom end drying the material out. If it was a very dry material or it was a very high hydrocarbon material, then we wouldn't need so much heat. We could operate that at about 400 degrees C, because the gassing point of high calorific value hydrocarbons is a lower temperature. It will break down more quickly. But this is fairly difficult textile fibrous material to break down, so we need that additional heat. So about 650 degrees C measured at the hot box is about the right temperature. Then the solid material that's left drops into this collection chamber here. The moisture that's driven off in the drying process flashes off in steam, wet steam, and that steam activates the material in here because it's nearly all carbon at that point. We're expecting that about 10% of the feedstock in mass is carbon at that point, black carbon, but there's still energy left in there. So by feeding the steam in there, we activate that carbon, release more energy, so therefore increasing the efficiency of the system. Then what's left drops into these twin ash screws here, and that will be similar to sand on the beach but dry. It will be a silica material, powder, light beige in colour, and that will be gathered up by these twin screws and transported out of the other side of the machine, which I'll show you in a second. The hot gas, the resultant hot syngas, which is the hydrogen, carbon monoxide and nitrogen, then pass through here and into that collection chamber there, which is a chamber that collects any dust, any particulate carryover is collected in there. Then the hot gas passes through that tube at the bottom there, and embedded in that tube at the bottom is a burner, and that burner is built in such a way that the methane, which is the carrying agent for the hydrogen, swirls and ignites. And the other tube that's coming off from the other side, I'll show you here, comes back to here. This is a fan. That fan is computer controlled because that is adding combustion air. So that creates the combustion ratio between air and gas, so that we can control the burn, so that the burn in that burner is as clean as it can possibly be by the computers operating this fan. This thermal oxidizer is the chamber within which the gas is burnt, and this thermal oxidizer can reach temperatures of 1100 degrees C. we will probably be running it at around about 900 to 1000 degrees centigrade, which is the temperature we need to burn out any microparticulate, which is the carrier media for things like dioxins, pathogens, furans, etc. So by burning at that temperature, we're burning out any contaminants, any toxic materials, any dioxins. So what comes out of the bike is clean heat. These two units here are auxiliary burners that are fed by the propane bank at the back, which I'll show you in a moment. These are there for startup from coal. These units fire through burners, the two burners there, two burner tips, to heat up the whole system. And when the system is up to temperature, then the computer, it's all sequence controlled by computer, this auto start. When the temperature builds up and the syngas is sufficient that the syngas burner kicks in, then these burners kick out and the unit operates on its own syngas, so there is no longer any auxiliary energy required.
How long is that period likely to be?
It depends on the material. This material takes a bit longer because it's wet, so that could take 90 minutes. This is where it's all controlled from. The whole unit is controlled from this multifunction touchscreen control panel here. Behind here are a series of PCUs and frequency controllers. Each motor has a frequency controller or a converter, so that each motor is infinitely variable in speed and torque. Now we can set these, and then they are controlled by the CPU. This is the auxiliary gas pipe. These are propane bottles. As you can see, at the moment we have two banks of 4 linked up to two separate manifolds, both are propane, and these feed through this manifold into these auxiliary burners, and this is purely for startup from coal. They're not needed during operation, because once the syngas is flowing sufficiently and at the right temperature, the syngas enters the thermal oxidizer through that tube. In the back of that tube, pointing into the thermal oxidizer, is a syngas burner, which is quite a large burner with a swirl device in the centre of it, which mixes the combustion air which is coming in here from the fan that I showed you on the other side. All of this is controlled by the computer. It's sensing the temperature, the flow, the temperature fluctuations of the thermal profile, so that it's cutting in the burner and the air to suit, because we can change the temperature of the burner, temperature of the flame I should say, by the addition of the air. These are the motors that drive the twin ash screws that I showed you on the other side, that pick up the ash from the bottom of the gasifier, and that drops the ash into this collection chamber at the bottom here, and then the ash starts its journey up this Archimedes screw, up this conveyor, up to the top, which I'll show you in a second. Now this device here is a closed circuit cooling device, water cooled. The water is fed through this cooler here, this chiller. And this chiller is a forced draft chiller with a big fan on the back, and it's pumped, circulated by this pump here with an accumulator and also pressure relief valves. So all the time water is circulating through this jacket to cool the ash. The reason for that is that the ash needs to be collected at the end of its journey, and we need to keep the temperature down for safety's sake. It's pure safety. It's nothing to do with technical performance, it's safety. I'll deal with this while we're here. The hot gas travels out to the top of the thermal oxidizer after it's combusted, and it's coming out of the thermal oxidizer at around about 800 degrees centigrade, and it's coming down through this duct and into the hot box, which is the outer jacket of the pyrolysis chamber, and it contraflows the solid material by flowing down. It then comes out through this duct. Now, under normal circumstances, at this point, this would be connected to an energy conversion device, such as a gas turbine or something of the sort, so that we can use the energy that's created to generate electricity, or district heating, or process heating, or whatever the energy is used for. In this particular case, we don't have a heat sink. There is no energy conversion device. So we've had to build this unit, and that is a heat sink. That is to discharge the energy that has been created in this unit, because this is really deemed as a test unit by the utility company. Now that device there is a cooling device. It's automatic controlled vanes to allow ambient air in to reduce the temperature of the air, so that we're reducing the temperature all the way up to the induced draft fan. The induced draft fan there, which I think you can just about see, that is operating at a very low speed, and it is creating a negative pressure in the entire system of between negative 0.45 and 0.55 millibar, so that if there is a leak, air ingresses, air goes into the system instead of gas coming out. But in addition, it maintains a flow all the way through the system, so that we know and we can monitor and we can control the different flows of gas by varying the speed of that ID fan. Now that ID fan, we try to keep as cool as possible. We want to keep it down to below 200 degrees C. Hence we have this chilling device, this air cooling device here. The stack that you see is not for combustion emissions, because there are no combustion emissions. That is purely for releasing hot air. It's purely for releasing energy, which would not normally be on a unit such as this, but we have nowhere else to put it. We have to dump the energy.
How much energy on an electrical scale would be generated by a unit of this size?
If the feedstock going in at the front end is roughly the order of 15 megajoules per kilogram and somewhere less than 40% moisture, then we can expect to consume roughly about half a ton an hour and put out roughly about 2.5 megawatts thermal energy, which would in normal circumstances produce about half a megawatt of electrical energy.
Okay.
Now if you come around this side, this is the drive facility for the pyrolysis screw. The pyrolysis screw runs up through there, and this facility here is because of expansion, because when you heat all this massive metal up, it expands, and we have an expansion device here that allows the whole thing to grow downwards as it expands. And we have to do that so that we take up the expansion in the materials, otherwise it would just lock up and it would buckle. Here is the ash collector. When the ash comes up through that ash conveyor, it drops down into here. Normally that valve will be open to allow the ash to drop into the receiver, but when you push this button here, then several things happen. That blade valve closes to shut this off from the system, and also we ensure that the cooling circuit is operating at full capacity, and then the interlocks will release on here, and this lid drops down. Inside there is the container. The container pneumatically drops, because usually it is jacked up and sealed, but it drops, and there are a series of rollers here so you can pull it out and discharge it.